So, hi, my name is Yubin Park. Can you hear me? Good. Okay. So, I'm really sorry for the people who were expecting Pradeep to present. It was very sudden change. So, I mean, fortunately, the session title was a inference from mixed source, right? So, I mean, I'm manifesting some mixed source of information from here. So, okay. So here I'll be talking about the categorical time series and some of the estimation methods. So categorical time series is everywhere. You can see from transaction history, disease history, all the kind of categorical variables that are related temporal orders. So here I'm presenting two very simple example. My friends Bender and Fry, they are buying Cokes and Pepsi crazy. So Bender, he's a very hectic guy. He buys Coke one day and then Pepsi, and he doesn't stick to one choice. And he buys Coke again, Pepsi, Coke, Pepsi. Okay? Now Fry, he's very loyal to one brand, and Fry buys a Coke and for 3 days, then change to Pepsi, and he just continuously buying it. So actually, there are a wide range of models that can deal with this kind of data, like a hidden mark model, SSM, where there are a bunch of different kinds of model. But here, I'll be talking about one specific model, and I'll be focusing on a parameter estimation on it. So the model name is a LavaCat, Latent Vector Autoregressive Model for Categorical Time Series. So here I have a very simple latent vector autoregressive model, xt equals c plus p, xt minus 1 plus some noise term. I have an observation which is linked, which uses this link function. Here I'll be using a multinomial logit function mainly. Noise model is typical Gaussian. So here I need to emphasize, basically this is a bit different from a hidden mark model, which has a discrete latent state. It's also very different from a state space model because here I'm using I have a categorical observation, not Gaussian. So strangely, actually, this kind of model hasn't been used that much. So another reason I didn't realize before I was writing the paper, but if you try to implement and estimate the parameters from this kind of model, it's very difficult. You have a categorical, basically a very limited number of observations and information, and you're trying to estimate the continuous parameter from it. Anyway, so how does fit this kind of model to Bender? So if I set c equals 0 and phi equals minus 1, it can capture this oscillating movement. And how does it work for Fry? So I set c equals minus 1, phi equals 0.5. It captures the decaying movement from one brand to the other. Okay? Okay, so now I try to estimate the parameter. In many of the literature, what we do is use maximum likelihood. Basically, y is the observation. I'd like to optimize the parameter theta. But here I have a latent variables, x. So basically what I need to do is I need to integrate out x variable. Unfortunately, x is not Gaussian. I have no closed form here. So basically, then I can expand out using the structure that is given in the previous slide. So this is the maximum likelihood function. There are also many different approaches to estimate this quantity, optimize and maximize this quantity. But here, once again, I'll be very focusing on one approach, which is an expectation maximization algorithm. So what is expectation maximization algorithm? So basically, I'll be calculating the lower bound of this maximum likelihood, and we'll be maximizing it. Okay? So using Jensen's inequality, I have this auxiliary distribution Q. So what I'll do is, basically, Q is not analytically obtainable. I'll apply a particle approximation, which is known as a sequential Monte Carlo or particle filter. So I get Q, then maximize this lower bound with respect to theta. So here is a simple, very brute force EM algorithm. And there are two issues. Okay? So basically, in the LAMORE model I presented, so the latent variable is basically an autoregressive process, which has very nice properties. But just maximizing the lower bound of likelihood does not capture the nice property of these autoregressive models. And it's also not scalable to the number of particles. Actually, I need to make some clarification about the scalable, because people use scalable to the number of data points, not the number of particles. But here I'm using scalable to a number of particles, okay? So here I'm presenting two tricks. So one is using asymptotic moment regularization, and the other one is incremental maximization step. So AMORE, this is not a contrived acronym for any random stuffs. So basically, from the previous example, when you have this specific type of parameter, so basically if phi is less than 1, this latent AR1 process is a stationary and ergodic process. What does it mean by a stationary ergodic? Basically, it's asymptotic mean. It's basically should approach to the sample mean in an asymptotic sense. Basically, from our model, so if we apply the multinomial logic to the y, basically it should be similar to this quantity. Basically, phi and c should be estimated from our algorithm. But in general, if we just apply the simple EM algorithm that I presented in the previous section, their quantities are quite different. So how do I make this thing happen? So basically, I'm interested in stationary time series, not stationary time series. So basically, I'd like to enforce some constraint on this. What I'm suggesting is I'm introducing a new likelihood function. So basically, here I have an indicator variable, is, which indicates whether the time series is stationary or not. I'm intentionally setting this to be 1. So basically, I'd like to estimate the parameter that, given that the time series is stationary. So this can be decomposed into this way. Basically, here I have, on the right side, I have a normal likelihood function. And the left side, I'm terming it as asymptotic mean regularization, which is basically AMORE. Okay? Actually, I'm not an expert on how the distribution would look like for this term. I'm just arbitrarily giving it as more like this below quantity. So you see, the meaning of this is basically okay, let's see. So asymptotic mean, so E over infinity is basically asymptotic mean, should be closer to the actual sample mean. So which is basically saying the ergodic process. Okay? Okay, I have given one constraint for the utilizing AR process properties. Then what about the scalability part? So actually, the maximization step is essentially solving a weighted linear regression. Basically, this can be solved at each timestamp using there are also a bunch of approaches, but I'm applying a Bayesian linear regression update formula. So this will be much clearer in the paper. So, okay. So basically, I have presented two tricks. Basically, one is applying the asymptotic mean regularization, and the other one is incremental maximization step. So they are the basically two key tricks for the LAMORE algorithm. But here, I'm giving one more additional trick, so exploring the structure of the LAMORE model. So actually, if I expand this model using a recursive way, basically, I have xt equals c plus phi xt minus 1 plus a epsilon t. This is basically, again, the C plus phi x t minus 2 plus epsilon t minus 1. So which is actually, I'm introducing two new parameters, CL and PL. And I have a new time series, which is parameterized in a different way. Again, I can estimate those parameters, CL and PL, for this low resolution signal. Okay? Then what I can do is compare the CL and PL to the other C and the phi, and whether they are similar to each other. Okay? So the reason of doing this is because there are a whole bunch of approximations here. Okay? Particle filter, or those things, MCMCs. So it reduces the particle approximation error, and actually, this AMORE can be overfit sometimes, so it reduces the effect too. So LAMORE is basically combining everything. It's quite complex, details in the paper. But after knowing all these key tricks, I think it will be very simple to understand. So, okay, so here are some experimental results. So BPEM is basically the baseline particle expectation maximization algorithm. And blue one is AMORE, and green one is LAMORE. Basically, low resolution added AMORE. Okay? So, of course, LAMORE has one more step, as LAMORE has a more computational time. But they are quite scalable with respect to the number of particles. But the BPEM, because we need to store all the particles over the timestamps, basically, it needs a lot of memory, hardware. And so let's look at the stability. So I generated arbitrary time series, categorical time series, giving a random parameterization, and measure the difference between two parameters, basically two parameter and an estimated parameter. And here is a mean squared error for those. Okay, so length of time series, I start from a very short one, 50, 60, 70, 80. So this result is for a binary sequence. And as can be seen, LAMORE gives the most stable parameter estimation results. So if you look at the how does it estimate it through the iteration, so this is quite informative to see. So basically, baseline, it has a certain gap because it's not utilizing the nice property of an autoregressive process. AMORE is approaching the true parameter much faster. So this result is for binary sequence. Let's go to the tertiary categorical sequence. Now it's totally mess. If I don't use anything about any properties about the autoregressive process, the baseline algorithm just overshoot anywhere, everywhere. Okay? So I need to regularize the time series and the estimation steps in somehow, and AMORE provides a certain way to do that. So, and what's the useful applications using these kind of things? There are a whole bunch of things, and here I'm showing two promising applications. So Medicare, Medicare is a national health insurance program for senior population in the US. There are three programs, Part A, Part B, and Part D. And Medicare Part D is basically covering the prescription drug. So I'm tracking drug purchase behavior of senior people. Basically, I'm tracking one person. So I categorize into three categories of the drug brands. Two major pharmaceuticals, Novartis and Teva, and the other. Okay, so a senior person typically has a lot of chronic disease. They purchase the drugs in a very constant manner. So here I'd like to do some prediction on it using this Lavaket model. So the baseline comparison here is a GLMNet using lagged features. I'm using two lagged variables, but the GLMNet actually doesn't have any predictability because this is quite difficult problem. So I don't know which kind of brand he will purchase in the next time based on the previous history. But this categorical time series can capture what kind of brand will be purchased. And if you look at the distribution of parameters, so basically I'm parameterizing. So I wonder whether I'm explaining clearly or not, but basically this Novartis fee and Teva fee, so it captures the brand inertia, okay? So as we have seen from the Bender and Fry example, so if fee is high, it maintains the previous purchase, but if fee is negative, it constantly oscillates between two brands, okay? If fee is 0, then basically that person's purchase is very random. So here I see the two distribution of brands parameters. So Novartis and Teva. Novartis has so interestingly, they have a mixture of something like Gaussian distribution here. One very random group and some loyal groups. But the more interesting thing is Novartis has a higher portion of very loyal customers, which explains why Novartis has a #1 market share here. Okay, so I'm giving a different example. So this is a Mimic2 data set, basically dealing with the intensive care unit resource. I'm trying to predict 3 cardiac conditions. There are sinus, tachycardia, arterial fibrillation, some difficult pronunciation, and the other, okay? So I'd like to predict. So here, GLMnet does something. Based on the previous data, you can predict some next cardiac states. But of course, this Lavaket model using this LAMORE algorithm performs much better. So here's a summary. Categorical time series and its latent variable model have a wide range of applications. And here I presented LAMORE algorithm that gives a stable and a scalable parameter estimation for very seemingly difficult type of models. And our model can be extended to cover more complex patterns, something like a stochastic volatility or nonlinear patterns, or I can have some control variables. Okay, so thank you very much.
So about non-stationarity, so have you considered the case where what if the model is a bit ill-fitting and the unobserved, the latent process would be actually non-stationary? So how that manifestate itself in the categorical variable?
So if the given time series is non-stationary, basically this model assumption doesn't fit. So basically here I'm giving a very specific model assumption that the time series is stationary. Usually that kind of assumption cannot be validated. I don't know whether there is a method to.
Well, in continuous time series, what you usually do is to use unit root tests.
Right, right.
So, but here you haven't observed the continuous thing, so perhaps it would be possible to make a generalized unit root type test that you first try to estimate the latent process and then see whether it actually has a unit root.
That would be very, interesting to see. Thank you.
Well, maybe briefly, I mean, you already mentioned, I mean, the kind of other possibility you could consider here maybe is something like hidden Markov models. So could you be a bit more specific about what is the advantage of your approach over?
Oh, okay. So basically, so I'll just compare with the hidden Markov model. So hidden Markov model, so if I apply to hidden Markov model to this Medicare Part D experiment, so basically I'll have several discrete states. But basically, then I need to specify what kind of interpretation to give all those states. The main advantage would be interpretability of the latent process. So you can interpret much easily, like a C is offset parameters, and a phi to be more like a brand inertial type of things. And more, the other advantage would be extendability. So because the latent process described in a very simple linear equation, you can give more additional terms easily using additional terms. So those two things would be more advantage compared to hidden Markov model. But the hidden Markov model is also very good. It has a deep history and research literature. That'll be interesting to see what are the pros and cons to apply both kind of models, I think.
Any more questions? If not, then let's thank the speaker again.